the primary clue given to man for revealing the mysteries of the universe. Light that often comes from a place so distant that it left its source long before the Earth existed. Light that has sometimes been traveling so long in space that whatever gave it birth no longer exists. Light from the stars and from our sun. Light reflected from our moon and the planets. Light which science has learned to gather, bend, break, polarize, amplify, refract. And other radiations too which cannot be seen. X-rays, ultraviolet, infrared rays, and radio waves. All gathered, measured, recorded, charted. Each portion of light fitting into the mosaic of a great mystery. The gathering of the clues, the fitting together of the pieces, is an ancient work, the science of astronomy. For 3 years, astronomers searched for a place where the clues of light could be gathered, a site for a national astronomical observatory. It must have clear weather and still air. It must be away from the path of dust storms, patterns of fog, vapor trails of aircraft, the lights and pollution of cities. The search covered 150 mountain ranges and ended at a peak significant in the religious tribal lore of the Papago Indians of Arizona. Here, where the Quinlan Mountains jut from the Sonora Desert, is Kitt Peak. Here, the Papagos agreed to lease to the astronomers a place to study the skies. For the astronomer's quest is in keeping with ancient Indian tradition, a search for answers which people of every time and every culture have asked. What is the universe? How did it all begin? How will it end? To this observatory, owned by the American people, come the questions from scientists and laymen, from philosophers and children. Questions from every part of the world.
Do you predict excessive flare activity for the coming week?
What mirror support system do you recommend?
Was there magnetic activity preceding the flare?
Would you send drawings of the interferometer?
Is it an off-axis paraboloid or spheroid?
Would you please send photographs of the solar telescope?
Well, when is solar maximum?
What's a star made out of?
And how do you support this theory?
Will multiple scattering affect the polarization?
What makes the sky blue?
Why couldn't we use a classical petrol, like this?
The whole problem is, where is the continuum?
The answers lie in the forces above us. Past and present events affect our understanding of the entire universe. The person who searches for those answers at Kitt Peak is far removed from that image of the astronomer of long ago, the bearded old gentleman in a swallowtail coat and stovepipe hat, spending the night on a high stool, peering through a brass eyepiece. Today, only the beard may remain. The swallowtails have given way to the parka and electric suit as protection against the cold night winds sweeping the open dome. The stovepipe hat is now often replaced by the hard hat, protection against the knobs, dials, pipes, and gauges protruding from the telescope. The stool is rarely used, simply because there is no more room on the platform. The brass eyepiece, in its place are sensitive radiation detectors and the photographic plate. But the telescope itself, for all its refinements and sophisticated instrumentation, remains basically what it has been since the 17th century days of Galileo, a device for the gathering and concentration of light. The 84-inch mirror at the National Observatory gathers the light of a star, making it more than 50,000 times brighter than it would be to the naked eye. This perfectly balanced instrument fixes in the astronomer's view a constant point in space, or tracks a planet on its own course as the Earth turns through the nighttime sky. This and a half dozen other stellar telescopes reach out from Kitt Peak for light from distant space. Light for scientists working with different questions and projects and problems. In keeping with the purpose of the observatory, most of the viewing time is assigned to visiting astronomers. And Kitt Peak maintains funds to provide financial assistance to astronomers and qualified graduate students. Modern astronomers spend little time actually looking through the telescope. They're too busy with instruments that can do the looking better than they can. Photoelectric photometers measuring the brightness and colors of the stars. Image intensifiers to electronically record objects fainter than the dark night sky. Spectrographs spreading starlight out into a spectrum revealing dozens of clues about a star: temperature, chemical composition, movement, speed. Much of the data from these telescopes is automatically read into computers, available for immediate readout or for later analysis with the observatory's central computer, making calculations in an instant that would take months of human mathematical labor. More important, the computer performs calculations so complex that they would be impossible to do by hand, regardless of how many years of labor were devoted to them. But all the exotic tools and technology cannot duplicate this, the creative process of a person thinking. And this is what much of astronomy is about. For there is a time when one must stare at the ceiling instead of the stars. Theorizing, interpreting, reasoning, speculating, probing the outer reaches of human knowledge in the laboratory of space so vast that mere instruments cannot cope with it.
What you want to know is where
In their particulars, the thoughts and theorems of the astronomer may be comprehensible only to another astronomer.
Is not to do anything more but to get the maximum sensitivity to an atmosphere, regardless of what it's made of and regardless of what its structure is. It's just to detect the minimum atmosphere.
Why would a person dedicate his life to studying the sky? The answer is very basic. It is in our nature to be curious, to try to push beyond the frontiers of understanding. Scientists travel beyond simple curiosity and find themselves on a journey marked by questions of time, of space, of the nature of existence. Questions which have marked the entire history of human thought. These are people who do not know where their search will lead them. They can only be certain that theirs is a quest without end. Two astronomers reflect on their work and their lives.
All the techniques we have today.
Yes, that frightens me, but I suppose it's really all right. Observations from space and large radio telescopes, and indeed the beautiful equipment we have here in Kitt Peak, have to keep all theorists on their toes. But after all, that's how we develop our understanding of the universe.
Despite all these techniques, that's the real exciting thing about astronomy, to understand more about the universe. The greatest rewards
that I've ever experienced have been the moments when I thought I knew something that no one else had yet discovered.
I sometimes think that we really can, indeed, learn about the secrets of the universe. It's certainly, sometimes one feels very discouraged, but even in our lifetime, I think that we may get the answers to some of the large questions that have been asked and puzzled people for a long time.
The discoveries made here become the property of all mankind. For not only is equipment and advice available to any qualified astronomer, but the findings are published, drawings, photographs, and designs are reproduced. Studies are passed along to all who request them. Many of the astronomer's answers, and indeed some of his questions, have application in fields far from astronomy. The nuclear physicist, the mineralogist, the life scientist, the ecologist, the aerospace specialist. The work of all is in some way affected by what the astronomer finds as he fits together the puzzles of cosmic events far from our Earth. Because of its mechanical and optical quality and the versatility of its accessories, the 84-inch telescope at Kitt Peak is one of the most powerful on Earth.
Okay, I'm ready. So, just keep the sun. Let's find it now.
The next time we come up, I'd also like to re-examine.
As powerful as this telescope is, it's dwarfed by the new giant on the crest of Kitt Peak. It was 12 years in design and development. Construction alone took 4 years. Kitt Peak's own engineers designed many of the complex auxiliary instruments. Most of them were built in the Kitt Peak instrument shop, where instrument makers could consult directly with visiting and staff astronomers, opticians, electronics technicians, design engineers, specialists whose requirements often demand of their art accuracy within unheard-of tolerances. As the dome took form, 19 stories high, the heart of the telescope was being prepared. A 4-meter mirror made of fused quartz, well over $1 million worth. 15 tons of fused quartz floating delicately on a cushion of air as it was meticulously ground and polished. The tolerance, 1/1,000,000th of an inch. A margin of error comparable to splitting a human hair 1,000 times. Three years of slow, painstaking, precise work before the mirror was ready to gather light from distant stars. The first of a new generation of large telescopes, the Mayall 4-meter telescope, was completed in 1973. Its 375-ton bulk so perfectly balanced that it is moved by a small motor. Its guidance system so precise that often during morning hours it detects thermal radiation from infrared stars it cannot see. Then locks on as the huge mirror gathers information about the evolution of these mysterious objects. During the day, technicians and maintenance crews prepare the telescope for the night work. When the astronomer enters the prime focus cage, he becomes part of the telescope itself. To grasp how powerful this instrument is, think of the dimmest star that you can see in the sky with the naked eye. The astronomer with this telescope can detect and study objects more than 4 million times as faint.
Okay, let me know when you're ready to start.
Okay, starting.
Good, we're going on a 15-minute exposure. Do you have the sensitometer on?
Yes, sensitometer is on with an aperture of 0.8.
Okay, and what filter are you using?
It's a GG495.
Fine.
This telescope was designed for rapid changeover of certain instrumentation, allowing more than one observing program a night. Successful innovations on this 4-meter telescope were incorporated in its twin 4-meter at the Cerro Tololo Inter-American Observatory in the lower Andes of Chile. Identical telescopes searching the skies over both hemispheres.
I think I had a pretty good run.
What is seen through the telescope is often spectacular, but advanced electronic equipment can reveal unseen clues in a photograph, giving each kind of information a distinguishing color, revealing to the astronomer details his eyes alone could not detect. Color holds the key to other secrets, too. To unlock those mysteries, scientists break the light into a spectrum by reflecting it off a mirror with thousands of tiny grooves on its surface. This special type of mirror is called a grating, in some ways more efficient than a prism. A grating is made by scribing the mirror surface with a diamond, ruling many thousands of parallel lines every inch. The machinery that does the job is one of the most precise mechanical instruments ever built. This microscopic task is so demanding that the expansion or contraction of metals in the machinery is a factor. The temperature of the laboratory must be controlled to within a few hundredths of a degree. The temperature inside the cover to a few thousandths of a degree. After 9 days of precise scribing, the diamond has traveled 17 miles across the grating's surface. Laser beams are bounced off the grating for a final check to see how precisely each groove reflects light. This is only one project of many for the opticians whose work is at the very heart of astronomy. Here, in the most complete optical shop known to astronomical science, technicians are constantly experimenting, designing, testing, working on new methods for gathering and analyzing light. To man, the most powerful light of all, the sun. This is the life giver, the source not just of light, but of warmth, of energy, of the essence of our existence. Yet we have only begun to discover its secrets. To learn the lessons the sun can teach, the largest and most powerful solar telescope on Earth has been erected at Kitt Peak. More than half its length is tunneled deep into the solid stone depth of the mountain. Sunlight. To us, 10 billion times brighter than the brightest star. At the big solar telescope, a series of mirrors gathers the sun's image, brings it deep underground, and places it on a table. Here, the sun is analyzed, the mysteries probed, the lessons learned. All from an image which comes to us from 150 million kilometers away, a point so distant by earthly standards that it takes 8 minutes just for the light to reach Earth. As a typical star, the sun can tell us much about all stars. And more, too, for the sun's energy affects nearly every form of activity on the planets, including the Earth.
Keith, I think the air mass is getting a little large. Maybe we ought to start switching over to something a little further in the red. That's all right. Speed's still pretty good. Yeah, it's up to 2.0 now. All set, Keith. Is that the freeze pressure yet? You just want the OG3 on that one, then, Keith?
The spectrograph breaks up sunlight into its component parts, a spectrum. Astronomers make minute studies of each portion of the spectrum and of the narrow dark lines that cross the background of color.
Something less than 4 millionths per step.
These stripes, called Fraunhofer lines, are the signatures of elements in the sun. By studying them, the astronomer can discover what the sun or a star is made of. Many elements have been identified in the sun, including the very fuel which it burns, hydrogen. There are enormous amounts of hydrogen in the sun, but the supply won't last forever. Astronomers now believe that the hydrogen will change to helium, and then, just as other stars have done, the sun will become unstable. It will expand violently. Its outer layers will engulf the Earth and most planets. Finally, it will cool. Cool and contract. Cool and contract. Cool and contract. But that is not likely to happen for 5 billion years. Until then, the sun remains the source of life and of knowledge of some of the basic forces at work in the universe. A picture that no human eye will ever see. The magnetic fields of the sun. And that is the primary purpose of this telescope, to learn more about magnetic activity on the sun. A mirror reflects the sun down the tower and through vacuum tanks, minimizing effects of atmospheric disturbances. By mapping the constantly shifting magnetic fields, daily photographs from the vacuum telescope help to direct solar observations by Skylab astronauts. Now, photographs are transmitted by facsimile machine to scientists who are attempting to predict solar flares. Those mysterious magnetic disturbances that garble radio and television transmission here on Earth and pose a major problem to space missions. There is so much in the future of this ancient science, a legacy today's astronomers will pass on to tomorrow's. Those who in the future enter astronomy will find it an awesome science. All the cosmos will be their subject. All of space, their laboratory. They will find their boundaries marked only by time. Time stretching back to the unknown. Time stretching forward, perhaps into infinity.
When I was a young kid, still in grade school, I used to read any science book I could get my hands on. And even then I knew that I wanted to be an astronomer. And it occurred to me that if we could learn more about our universe and where our sun and our Earth and where we fit in, we could understand more about us. What are we? Are we unique? Are we alone? Where are we going? And why?
Produced by the Association of Universities for Research in Astronomy under contract to the National Science Foundation.